So it's a great pleasure to welcome Irfan Siddiqi to the JQI seminar. He's one of the leading researchers in quantum science with superconducting circuits. In fact, he worked on superconducting circuits before they became the sort of large qubit systems that we know today. He did his undergrad at Harvard and a PhD and postdoc at Yale. And now he's professor at UC Berkeley, where he founded the Center of Quantum Coherent Science. He's also the director of the Advanced Quantum Testbed at Lawrence Berkeley National Lab. And he made a number of seminal contributions to the field, including the development of quantum noise limited amplifiers for microwave frequencies. And he is also implementing quantum circuits with superconducting qubits, and is researching sort of more fundamental quantum physics effects like wave function collapse. And so also some of us at the JQI have a new connection with him because the director of the sort of the new DOE Center Quantum System Accelerator. So we look forward to collaborating with him more in the future. But first we look forward to his talk, which is on improving the sort of reducing the noise of superconducting circuits with randomized compiling. Irfan, welcome.
Thank you, Norbert, for the very kind introduction, and thank you again, Alicia and Charles and Vlad and everyone for the invitation. Can everyone hear me okay? Maybe you just do the thumbs up, thumbs down thing for the usual Zoom vote. So let me go ahead and share my screen. Let's see if you can see this. Okay. Turn this into a laser pointer. All right, how's that? Can you see a screen with a little green dot?
Yes.
Okay, very good. So I picked this title, Extending the Performance of Noisy Superconducting Quantum Processors. So I thought it had a very quantum information feel to it. But I think what I would like to sort of start off with is say that really we are still studying, I think in my mind, at the academic scale, fundamental quantum physics, right? And basically the extent to which quantum theory applies in its current form. And I think that drives lots of us. And that's not to say, of course, we're not interested in quantum information science, but I'll show you a little graphic by what I mean in a moment. So first, I like to pay homage to the current team. So we have a mixture of engineering staff, research staff, postdocs, and graduate students. They are listed here. The folks listed in red are the ones that I will typically steal from in terms of their hard work in this talk. And I will sort of restrain myself, I think, for most of the talk to this little manuscript paper that we've put out very recently on the archive labeled at the bottom right. So you can refer to that going forward for additional details and supplementary material. So it's really Ravi and Akhil that have done this work, and John Mark has been our fab guru for a long time, and I will also reference his work. Okay, so here's what I mean by this. There's really a coin that on one side is quantum computing, but on the other side is quantum foundations. And quantum foundations, of course, for a long time was relegated to the Friday session of the March meeting, right? In the absence of tools that we had to actually approach this field. But we see something quite exciting happening, that with the development of quantum information devices, we have really new tools to ask very basic questions in quantum mechanics. So I wanted to give you sort of a brief 40-year history of what's been happening in this field, right? Sort of shown here on the left. In the 80s, people were really asking the question, well, are these circuits actually quantum? After all, quantum mechanics really was born in atoms and physics, atoms and photons and ions and so on and so forth. Now you have these big things which are electrical circuits that have voltages and currents. Do they really obey the same quantum mechanics that these atoms and photons do? And one refers really to the canonical circuit on the right. It's just an oscillator, right? Shown in green is a Josephson junction, which is an inductor, right, shunted by a capacitor. And after all, this oscillator feels some kind of damping through a resistor. Okay, that's really the circuit we're looking at. And if you sort of cool to very low temperatures, you are able to see the quantization of this oscillator, which typically falls within this 1 to 10 gigahertz range, given the devices we have today. So in the 80s, Leggett was raising these questions of macroscopic quantum coherence, and they led to a very nice set of experiments on Josephson junction circuits, where by the time you hit the 90s, we realized that if you really decouple very strongly from the environment, you try to hide your circuit as best you can from this resistor, you start to see signatures of quantum mechanics, right? You start to see the spectroscopy. You can make out these levels that are there. But as you can understand, that's good from a quantum foundations point of view, but from a computing point of view, you've hidden your circuit. There's no real way to control it. There's no real way to read it out with high fidelity. So around the 2000s, we see the first charged qubits coming into existence. And now you can go ahead and control quantum systems, albeit the measurement was not very good. You were measuring ensemble properties at that time. And then sort of fast forward another 10 years, and we have the ability to now do high fidelity single shot measurement and trajectories and so on and so forth. Again, going back and forth with this idea of new techniques for fundamentals, also serving quantum information science. And I think the tremendously exciting boundary that we're seeing now is when you go beyond 1 qubit to many, many, many qubits with this control, then what does this many-body entanglement look like? And in particular, we're testing quantum mechanics really in a new region of open quantum system where you have many degrees of freedom that are there. So that's my introduction, I think, to the subject and how one can view the two sides of any of these experiments. Okay. So I want to sort of raise a few contemporary questions that will be the subject of the talk today. So pictured on the left is one of our older yet workhorse quantum processors. There's 8 qubits on it. So let me walk you through this. So each one of these little boxes, you see the capacitor, the transmon qubit, the junction is quite small. So you can see 8 of these boxes, 4 here, 4 here, okay? And they are connected in a ring. Okay, so you can follow the little green dot. That's the ring that connects these 8 qubits in this topology. Each one of these qubits has a little resonator for readout. So you're doing this cavity QED type of measurement. So this little meander here. And that couples to a bus. So this is another resonator shown in this topaz type of color, which goes off the chip onto a series of superconducting amplifiers for measurement. So the readout is multiplexed with different frequencies, and each of these qubits has a drive line labeled here D. Okay. Now the coupling between qubits.
Irfan, may I ask a question?
You may
on behalf of the civilians? Where does the word transmon come from? Did it predate the quantum QED? Is it an old word for a well-known superconducting device?
The history, Vlad and others may comment on it. As far as I know, at Yale, it's more of a combination of a transmission line, right, and a plasmon of sorts. So that particular origin gives you this type of mode of the qubit. Do you agree, Vlad? That's sort of your understanding of the transmon in the Yale era when you were there? He may not be as, or Alicia, do you want to chime in?
No, well, what Andrew always, Andrew always said was that that's where the name came from, was sort of adding a transmission line to something. But then he would always add that the final incarnation kind of had nothing to do with the transmission line, but the name stuck.
Irfan, from what I heard partly from Michelle, is that it more has something to do with the way unharmonicity transitions from positive to negative. So that trans was more like that kind of transition, because a Cooper per box has a smaller frequency 0, 1 and a higher 1, 2, and then as you keep reducing the charging energy, it the 1, 2 becomes lower frequency than 0, 1. And so at Lezouche in 2019, there was a discussion of that, and that's the latest I heard.
I see.
Well,
so
I'll ask the editors of the Oxford English Dictionary to contact the both of you and get it all sorted out.
So Charles, I think basically this will be a mythical animal. After certain numbers of generations, it's not clear what the origin is. So I think what one can say with clarity, though, it's an LC circuit. So it's basically an oscillator. And I think that may be sort of the most descriptive piece of that. But it has, yes, something to do with transmission lines, something to do with the anharmonicity, something to do with plasmons in the circuit, looking at the sloshing mode. Okay, so those are the simple LC qubits that are LC circuit qubits that are there. And what's becoming interesting is, aside from the quantum algorithms you can run, this quantum processor realizes a flexible test bed for studying noise and dynamics in a 100-particle bath. So you see, typically with superconducting circuits, we were in the model of here's a junction coupled to some very complicated environment, which is causing decoherence. Your environment now is perhaps the other qubits on your chip, right? And they can sort of become a larger number. And this is, of course, very much in vogue in cold atom physics, where one engineers an environment around your qubit. And one can then look at how information is lost in such a system and look at all the different processes and study the correlators in extent quantum systems, etc. So The one twist that I want to put on this is that quantum computing utilizes information theory to study the physical world. So if you have this large arrangement of quantum objects, how do you study them? Right? There are certain NMR methods that tell you what the noise is. There are other condensed matter methods to study statistics, etc. So quantum information has its own language, so to speak, to probe this kind of many-body physics through both random circuits and algorithms. And I think this is a very powerful field of theory, of course, as we agree upon, that goes ahead and gives us new probes of the physical world. The prerequisite is that we have to, in the solid state, get beyond a regime where you are limited by local sources of decoherence. So for example, if there are little films or other defects on your chip that immediately cause the quantum coherence to go away, then you don't have a lot of room to see what that many-body quantum effect is. Right. In fact, all the information is lost very rapidly to degrees of freedom that you don't access. Okay. So in particular, one also has to think about extending that beyond 1 qubit. Right. We'd like that robustness and high coherence to exist in however big your chip is and from chip to chip. Okay. So the outline of the talk is I want to just show you a few slides on sort of the current process for building these qubits that we have, excuse me, that yields coherence times regularly above 100 microseconds in 2D planar devices, and also allows better than 2% frequency spread on a 6-inch wafer. So if we want to target a certain frequency for a transmon or a transmon circuit or a qubit circuit, we can do that. With that in hand, then I want to sort of transition on to how do you reconstruct the noise, okay, in that particular many-body system? You know, what are the quantum information tools to figure out, or at least start to figure out what your noise model is? And then the flip side of that is, with that noise information in hand, in number 3, can I tailor the noise to extend the depth of quantum sequence that I can run? Okay, and again, showing you with between 2 and 3, understanding the fundamental noise piece is the physics piece of this, but then again, there is an application in number 3 for that. Okay, so moving on to the first topic. So the bad actor, at least the major bad actor in this particular circuit, are oxides on surfaces. So the circuit is a tunnel junction, but of course it's connected to wires, which are superconducting transmission line of sorts. So here's a prototypical coplanar waveguide transmission line. The orange type of metal here is niobium on a silicon substrate. And there are places where films grow that are highly unwanted. For example, in between the metal and the substrate, in the gaps between your metal leads. And of course, Kevin has studied this in great detail amongst others, trying to figure out what are the losses of Q and fluctuators and so on and so forth. What we've been doing over the year and a half or so is to combine the technique shown in the upper right, where you do electron microscopy, both scanning and tunneling, with analytical tools to figure out what is the actual structure, right, of the metal, of the oxides, etc. We do it in tandem with X-ray photoemission spectroscopy, XPS. This allows you to get the thickness of these layers in a very accurate way. You combine those two tools with electron probes that are dispersive and fluorescent-based to figure out what is the elemental composition of these layers. And finally, you want to, on the same sample, measure the quality factor or the lifetimes of your qubit. So in this particular case, I'm showing you a resonator study. So if you look in the centerpiece here, this is a 100 nanometer scale bar. You can see this niobium on silicon interface at a step edge. This is showing you the edge of one of the conductors of this coplanar waveguide. You can ignore the white metal on top. That's the carbon and other things you deposit to do the TEM. All the action is happening here between the niobium silicon and the interfaces. The interface between niobium and silicon as we grow it is actually quite good. So you can see here, here's niobium on silicon 011 on a 5 nanometer scale bar. You don't really see a lot of other elements occurring here. So this particular interface for us seems to be working very well. If you look on top of the niobium, there you now start to see some bad actors coming in, right? So you see niobium oxide growing, a healthy layer of it. We can actually also figure out how much oxygen is in this niobium layer as we go on top. And in fact, you can figure out all the different oxides of niobium, and there's a lot of them. So NB205, NBO, NB204, etc. So we can figure out in this color map which particular configuration of niobium that we have on there, and also try to then correlate its loss. And similarly with the silicon surface, you can very easily identify it here, the silicon oxide and its different isotopes that grow. So we can pinpoint loss now from niobium oxide, silicon dioxide, silicon oxide, We can correlate the thickness with the loss. And in fact, we reliably get now Q well over 5 million at the single photon level in resonators that we build. So not all of these have been incorporated to our qubits, but we are steadily doing this. And I think there's another interesting piece of this. We can start to identify losses that are not two-level systems. So in fact, they don't have this typical power dependence that you would see in fermionic defects. So just to give you a sense that with the tools coming together in the large team, we can start to make progress, at least in identifying some of these layers. The next piece of this is how uniformly can you make junctions? So what we're showing here is that exemplar qubit that I showed you that had 8 qubits on it, that processor, that's represented by one of the squares here. Okay, so each one of these squares, you can see 8 little rectangles. Those are sort of the properties of those individual 8 qubits. We put 64 of them on a 6-inch wafer. Okay, that's what's shown here in the entire square here. We automatically probe them. It takes a night. This was a great invention, reduces a lot of graduate student labor where it automatically probes the entire wafer overnight to give you resistances and parameters. And what I plotted in the color here is what is the frequency you would expect for this type of qubit in the color code. And I've shown you histograms for each one of those 8 qubits here. So for example, for qubit 1, QB1, this frequency range goes from 4 gigahertz to 10. And indeed, we were trying to actually hit only a single frequency, but you can see the histogram is all over the place. We would have gone from 5 gigahertz to 8 gigahertz in this qubit. The same for the other one, the same for all the other ones. So this was telling us we have quite a spread in the resistance of these sub-micron or 100 nanometer junctions that are there. So you can fast forward 36 wafers where we've put in the following improvements: differences in development, differences in how we do the ash, differences in how we actually oxidize the barriers, etc. And you can see the result is on the bottom. So this is a much more highly uniform distribution of resistances that's shown in the histogram here. And finally, you can even see a little bit of a curve, right, in these frequencies. That's by design. Okay, we actually wanted to offset the frequencies a little bit to run the cross resonance gate in this case. So you can see that little sine wave. So the upshot of this is this puts us in a position where you can start to study now, not disorder due to the physical properties of your qubits and not decoherence due to very short lifetimes. Okay, in particular, we can start to think about other methods of decay. And just to show you the stability.
This is Bill Phillips. I'd like to ask a question about that previous slide. So this is the distribution of frequencies among the many qubits that are on this chip. How stable are these frequencies? That is, if you measure them again an hour later or a day later or a month later, are they going to be the same?
It's a great question, Bill. In fact, I'm going to show you some of the stability data in a slide. The frequency is actually quite stable. What typically happens is if your fridge is cold for extended periods of time, and we run for 6 months onward, then you can definitely stay pretty much parked where you are, much better than, let's say, 1%. However, things may happen. If you have a cosmic ray or some other event that happens, all of a sudden you'll see a step function, right, where there will be a switch in your frequency, or somehow, as is common in California now, you will have a power outage. So as soon as you warm up the fridge and cool back down, then they're going to all shift around.
Well, one of the things, I mean, that's behind my question is, how stable is the frequency going to be during a computation? And of course, one hopes for computations that are longer. And so what about, you know, on a time scale of milliseconds or seconds even?
Yes, so I would say on that time scale, they're extremely stable. The bigger thing we suffer from, Bill, are fluctuations in the coherence parameters, which can vary by hundreds of %. Okay, so you can have let's say a T1 of 100 microseconds, and it will cut out to 10 microseconds. Right? And that spectrum is quite troublesome. And in fact, I would like to figure out what that source of fluctuation is, because it's sort of right in my face. Right? I build a circuit and it's not varying by like a part in 10 to the 6, it's varying by 100%. And I think that's definitely what we're trying to target soon. But we are making progress on that. So let me show you this slide. Yeah. So this is a plot of, let's say, of one of those qubits, Q3. And I'm measuring T2 in this case. This is with an echo sequence. And you can see there is a distribution, and it's 132 microseconds on average to a Gaussian fit of plus or minus 8 microseconds. So this for us is typically pretty decent. And this is measured over 2 hours. Okay, that's here. And I can build the same map for T1 and T2 on all of these qubits. And those ellipses give you a sense of what that stability is. So there is definitely width, right? It's better than the 100% width that can be seen on bad devices, but still there's some science to be done there. Does that help a little bit, Bill, understanding the stability of the device?
Yeah. Thanks.
Yeah. And again, it's, as you say, it's a question of, how long the full computation would be. I'm going to show you circuits that are sort of order hundreds of microseconds. So overall, at least we, on a 2-hour time scale, we can be reasonably stable. But it's a very big issue. We would run, let's say, a quantum simulation for scrambling that had lots of gates, and at some point, something will cut out, right? And understanding what that is rather critical. Okay, so that was my introduction to part 1, showing you the lifetimes, just to give you a sense of where these lifetimes scale compared to current processors. The older chip that I'm showing you is still where that red plus sign is to the right, which is rather competitive with things that you see in the commercial domain, and other qubits, if you pick your favorite qubit, etc., can be much, much longer. This is sort of average value shown here. Okay, so moving on to noise reconstruction, cycle benchmarking, randomized benchmarking, all of these things. Again, ways to study the structure of noise in your physical system. So let me start first by saying that there are errors and there are errors, and they are different. Okay, in particular, trying to draw this distinction between coherent errors and stochastic errors. So the model that I want to use, let's just think of a single qubit. It lives on a Bloch sphere, typically shown on the right. States that are on the surface of the Bloch sphere are perfect, pure quantum states, right? They have unity length of the Bloch vector. States which are mixed or have some other statistical character shrink from the Bloch vector that's there. And you can imagine a coherent error as a mechanism which causes you to sort of lose your coordinates on the surface of the Bloch sphere. So let's say you wanted to rotate to a certain angle, but you sort of misrotate. You rotate too much or too less. So that's sort of just putting you in a wrong spot on the surface of the Bloch sphere, but you have not lost the purity, so to speak, of your quantum state. So these types of errors can arise from imperfect unitaries, from miscalibrations, from drift, or from crosstalk, right? So you're driving one qubit, but some part of your control pulse leaks to the adjacent qubit, and it makes you move on the surface. So this maintains quantum coherence. What's interesting is sometimes they can, most of the time they will hurt you, I imagine, because of Murphy's law, but sometimes they can actually help you, right? You may have some coherent errors that actually put you in a better spot relative to the average. So they're rather unpredictable. That's really the point to take away. You run an algorithm and you have coherent errors, and they give you basically a big spread in the performance that you'd have at the end of the day after running many gates, say. They also have a quadratic impact on accuracy. So if you have lots of coherent errors that are concatenated in a sequence, they will indeed hurt you very badly. And I'll show you some examples of how to calculate back of the envelope what's happening here for thresholds. Compare that with stochastic errors. So it's a stochastic error is interaction with a noisy environment. So here the intensities, in fact, are adding rather than the amplitudes. So pure dephasing is an example of that, where you just wander around, let's say, the surface. These types of errors do not maintain quantum coherence. You can have a shrinkage of the Bloch vector, shown here, going into a mixed state. They have a linear impact on algorithm accuracy. So even though you are actually interacting with a much larger bath and going outside of your computational space, which is on the surface, let's say, of this Bloch sphere, nonetheless, they accumulate in a way which is kind of friendly, relative at least to coherent errors. So that's to draw the distinction between these two mechanisms.
Okay, Irfan, I'm a little bit confused about the distinction between these two errors. I will often tell students when talking about the difference between pure states and mixture states, that if somebody was preparing a pure state and giving it to you and didn't tell you what the phase, for example, of a let's say it was a 2-level system, and the person prepared it and knew exactly what the preparation was, so that as far as that person was concerned, it was a pure state, but introduced into it a random phase that the preparer knew, but that you don't, then if the preparer does that repeatedly, each time giving it a random phase that the preparer knows and that you don't, there's no way you're going to tell the difference between receiving something that is in fact not a pure state from a preparation that produces a density matrix rather than a pure state. So I'm not really understanding the difference between what you're calling coherent errors if you really don't know them, as opposed to stochastic errors.
Yes, so you're absolutely right. It depends on, in fact, what basis you look at and what your measurement is. So this, for me, was an omniscient observer, making the very simple difference that your block vector, if you knew it ideally, is of unit length or smaller. So of course, how you cast that in a reduced density matrix, you're right. You would only be able to tell one or the other. And that'll be part of the story that comes later. How do you actually distinguish between these two errors?
I mean, it sort of reminds me a little bit of the cubism view of quantum mechanics that has to do with how much you know, which of course varies from observer to observer. But
that's right.
Are you trying to draw the distinction, for example, between classical noise and quantum noise here?
We will do both. So hang on. So for example, to answer the dichotomy that you're showing, there is a very well-defined concept of the length of this vector, right? Either it's length 1 on the surface or shorter. If you look at its projection, yes. So if I look at the projection of this, it will look smaller, right? So that depends on the quantity you're measuring. But I'm just saying that you can have vectors that operation that preserve length versus not.
Well, I guess what I'm saying is that I'm not sure that difference is clear, just as you said, depending upon who's doing the looking, whether it's the omniscient observer or whether it's the ignorant experimentalist.
That's right. And we will see that in a moment. And we will see, in fact, methods that, in fact, exactly do as you say, that cannot distinguish, and other ones that sort of try to pull that apart. So but you're absolutely right. It's very much, in fact, a key part of the talk will be, what is it that you're measuring? Right, because different metrics produce different results, and that's very critical.
Well, that always seems to be the answer to difficult questions in quantum mechanics. What are you measuring?
That's right. That's right, and those are the questions I love. So I love this question.
Okay, thanks.
Sure. So let me. Again, I showed you the chip. I walked you through it. This particular is an older version, right? But T1, just to give you a sense, was 70 microseconds on this echo time, 90 microseconds. We were measuring 4 of them in this particular experiment. I'll show you 4-qubit circuits, Fourier transform and otherwise, so that gives you a sense of the size of what we're using. The native 2-qubit gate that we're using is a CNOT, okay, done by cross resonance effect on pairs of qubits. And what we start off with is exactly what Bill was saying. How do you know what error you have, right? How do you measure it? And we suspect that there's significant coherent error due to higher transmon levels, okay, coupling between states that are there. Always on coupling and microwave crosstalk, but no way to know, right? And distinguish these things from other error mechanisms. So let's try to piece the story together. So the first technique, which has gotten quite a lot of mileage in the community, is something called randomized benchmarking. So I want to sort of spend one moment on this slide to give you a sense of what you're trying to measure in this routine. And that will also allow us perhaps to do randomized benchmarking plus. So if you look in the literature, there's many different randomized benchmarking protocols, XRB, cycle benchmarking, unity benchmarking, so on and so forth. And I don't know, at least personally, I'll just track sometimes of what all of those are. So let me start maybe with the vanilla version of this to sort of motivate what one is trying to do. So you start off with the state, right, shown here, and then you measure the state at the end. So if you were to do just this operation, I prepare a state and I measure a state, you're already subject to error. Right, you're subject to error in the preparation and you're subject to error in the measurement, okay? So that gives you a baseline of what your error would be. Into that sequence, you insert a set of gates, okay? C1, C2, all the way up to the last gate here. And what one can do in vanilla benchmarking or randomized benchmarking is you go through all of these gates except the last one, okay? And then you undo the effect of the previous gates in one gate. So let's imagine you were doing a single qubit set of rotations. You rotate, 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 right? Keeping track of what you were trying to rotate. And the very last one, you undo the product of all those rotations. So you've made now a very complicated identity, right? You've basically taken excursion and you come back. And as you increase the length of this identity, since your quantum state is changing along the way, then you see a decay of the output at the end. right? So you see a decay of the probability at the end. So you apply a series of random gates. And so the critical part will be to make sure you sample these gates from something that gives you some knowledge or some accurate sampling of all the gates in your set and all the errors that are there. So in the modern day, we don't do these hard random unitaries. We're typically using Clifford group operations, a bit easier to do in quantum computing. But you apply a series of gates that realize an identity, you can become insensitive to preparation and measurement errors because you're just seeing, relatively speaking, what the decrease of probability is. And you average over many sets and you get an exponential decay. Okay. So this is a very popular and simple process, right? It gives you a sense of what is the accumulated error, which if you divide by the number of gates will give you the error per gate. Okay, so you get one simple number. It is simple, but of course it hides, as Bill was saying, what are the types of errors you have, what's the distribution of errors, so on and so forth. And in particular, it works because it actually takes any noise process, Bill, and puts it into a depolarizing noise. So this is sort of the decimation that happens with this type of randomization protocol. So the one caveat that I want to put on this, that's the typical vanilla RB sequence. SRB is popular in the literature. This is sort of streamlined randomized benchmarking. And what you're doing, it's basically the same idea. You are not going to undo the effect. Okay, so you're going to put a series of gates that should have some known Pauli rotation. So I put a bunch of gates together. It should have some kind of Pauli operation at the end. And I'm just going to measure the fidelity of my output. So I should get a certain Pauli term, and I see what the fidelity is, and I see the decay of that fidelity as a function of length. And that allows you to fit it to a simple form that says I have some coefficient which says what this reduction of my amplitude is times this process fidelity taken to the nth power if I have a sequence of depth m, right? So I keep applying this process and measuring the decay of the Pauli operator. And that literally is what's shown here. I wanted to sort of make this distinction between, this vanilla RB and SRB, because in fact, lots of things can be done in this averaging over Clifford set model. Right. So in this case, what I'm now measuring is a process fidelity for each one of these circuits and seeing how that decays. And later, I'm going to start to measure, in fact, some unitary operations and more complicated gates and see how they decay and so on and so forth. So it's the same principle that goes in all of these randomization experiments, just for different quantities that you're looking at and looking at their decay. Okay, so that gives you a sense of, in this case, I'm running actually a 2-qubit version of this. It's a 2-qubit gate run on 5 and 6, qubits number 5 and 6, and you can see the decay of the fidelity. Now, so RB in this sense takes all your errors, irrespective of the error model, and puts them into this kind of depolarizing noise that reduces the length of your block vector. So it's really underestimating the impact of coherent errors. As we'll show you, coherent errors can be very nasty, right? In a particular algorithm, if you thought the only error you had was the stochastic noise, you would be in for very much of a surprise, right? In this case. So we need to actually increase the sophistication, if you like, of these randomization protocols to sort of distinguish between different error models that are there. So the first step towards this was really proposed by Joel Wallman in 2015. This is called unitary benchmarking. And what one does is you basically measure the purity of your state. You measure the length of the vector after each sequence and see how that decays. And you can compare that number, which only looks at decay of the length of the block vector, relative to the full randomized benchmarking, and you get a budget, right? Between what is the total error and how much of that error actually is coherent error. So that's what's shown here. So these numbers are interesting to look at. So this is simultaneous 1-qubit gates, okay, and 2-qubit Clifford gates. So for the 4 qubits that are shown here, and these are 3 pairs of qubits that you would run a CNOT gate on, for example. So the overall error rate is shown here in powers of 10 to the minus 3. And this is the fraction of that error that is actually the coherent error that's there. So you can see it's quite significant, right? Because we've tried to do a good job here of reducing the dephasing, decoherence, et cetera, in the system. But in reality, you actually have quite a large coherent error rate, which is here. So that's the first step of this, saying that you do have coherent errors. Now, can we say a bit more about what actually are those coherent errors? What is the actual process that's happening? Which qubit is talking to which qubit in the environment? So one extends this now to something called benchmarking cycle errors on a QPU. And there was a beautiful paper by the ion trap group of Rainer Blatt a few years ago showing, in fact, how one applies these kinds of cycle techniques to a extant qubit system. So let me, in fact, start with the picture here. So you'd like to actually understand some kind of process shown here by G, okay? So some G, which is a gate, which actually connects multiple qubits that are there, and you'd like to run it and see what are the errors and what are the specific errors that occur in this process. So you have to do a few different things. The first thing you'd like to do is, again, remove the effect of your preparation and measurement errors. Okay, so you interleave it then with these P's. So these P's are, again, this kind of randomization operation, as I showed you in the previous slide. And what that does is it maps all the errors onto poly channels in the same way that randomized benchmarking does. Okay, and then on top of that, you put in operations B and B prime, or B twiddle here, that are different poly rotations. So in fact, you want to run this sequence, G, remove the errors by poly twirling, preparation errors, and then you put in a certain input state and you measure a certain output state, and you want to see which one of those states actually causes your process G to go bad, right? And that gives you a sense of how sensitive you are to certain poly channels of error. Okay, so here's the process flow. So in this particular case, what I'm going to illustrate, I'm doing a C0, okay, between qubit 5 and qubit 6, and I'm going to leave 4 and 7 idle. Okay, so that's sort of a typical 2-qubit gate. And naively, you would think, well, 4 and 7 are idle, they shouldn't be doing anything to my qubit. And it's absolutely not true, right? In fact, the dominant set of errors are on your idle qubits, because in fact, you're not controlling them. So what one does in this cycle benchmark is you measure a cycle, right, with different poly inputs, and you can map on to, depending on your poly inputs, you can try to look at single body decays. So for example, are my idle qubits staying in the ground state or the desired state, or are they rotating around? I can look at 2-qubit decays, 2-body decays, you know, what's happening between a pair of qubits. I can look at what's happening to the C0 decay. I can look at any complicated correlator that you want to make, right, between the C0 and another qubit, so on and so forth. So let me walk you through a little bit of the flavor of this type of information that you get. The color code is telling you the error rate. So in this heat map, this dark bluish, purplish kind of color is very low error. Yellow is telling you that's much greater error. So the cycle of interest, you see 3 columns here. This says I'm trying to run a C0 gate between 4 and 5. I'm running a C0 gate between 5 and 6, or I'm running a C0 gate between 6 and 7. That's the cycle of interest that I want to sandwich between these different poly operators. So now if I run this particular sequence between 4 and 5, I'm going to look at what is the error on qubit 6 in Z or X. And you can see there's almost very little error, a little bit of error in qubit 7. But in fact, when I run this particular pair, it's totally different, right? The coupling is different, the errors are different, the magnitude is different. And you can continue. What's the 2-qubit error, right? What's there in Z, X, I, or ZZ, which represent the dipole coupling between the qubits when I run a C0, so on and so forth. So this is a very, very precious fingerprint telling you, in fact, which poly channels are participating in the coupling. Now, you can do several things with this. You can take this kind of map of correlators and in step 1, undo it, right? So if I know, for example, what the error is, I can design a pulse sequence that will undo it, right, every time and turn off these cross couplings that are there. And that has been tremendously useful in trying to run longer sequences in quantum information science. The other utility I think that we have not explored yet will be, how do these errors decay both in time, as Bill was asking, and also in space, right? As you go ahead and look at coupling across space, do they scale in a way which actually is compatible with fault tolerance, right? We don't really know, in fact, how these error mechanisms scale in space. So again, a nice laboratory to study with a little bit more detail than the vanilla RB I started off with. What are the particular sources of error and mechanisms on your chip? So in the final 9 minutes, can you do something about this now that you actually have a sense of what errors are doing? And this leads me into this protocol called randomized compiling. And it's very much based on all of the ideas that I mentioned in the previous slides. So what have we recapped with errors? The accuracy of algorithms are impacted by errors. Coherent errors and stochastic errors are there, and I will show you how they impact actually the depth of circuit you can run and why they accumulate a bit differently. And what I want to show you is that you can add randomization to, in fact, reduce these errors, because you can, in fact, convert the errors that you have in your system that are coherent to stochastic errors. Okay. And you can measure them with the scaling of your properties of your circuit. So that gives you a quantum information way of trying to distinguish between these two errors. So what does the protocol look like? Well, here's 5 qubits shown here. This is the standard notation where the horizontal line tells you the life history of a given qubit, where the life history of one qubit meets another qubit is set by lines in the vertical direction. So in qubit number 1, I run an X gate, a T gate, and then I'm participating in some C0 sequence, a Hadamard, and I measure, so on and so forth. Okay, and these are examples of what you could do. If I now insert these randomization gates, so let's imagine I go ahead and twirl the gate that's here with an X, with a Y here, and then I want to undo that effect a little bit later. So much like randomized benchmarking, I was inserting a series of gates and then undoing it, right, in some way. Here I insert a Z gate, but now I have to undo its effect through the C0. Okay, so you get a bit of a different gate. So you start adding all of these random gates and undoing them. So at the end of the day, they should have no effect on your output circuit. It should be equivalent. Okay. The nice thing is you can recompile all of those rotations. After all, this is a compound rotation if you put them together. So might as well just compile them together. So that doesn't increase the depth of your circuit. Okay. But in fact, what it does, it will change the error characteristics that you have. Okay, so let me illustrate how that happens. So let's imagine the black is the target state that you want. That's an ideal quantum state that you want to be in. Okay, unfortunately, you're unable to rotate from some fiducial point in the Bloch sphere, so you're off by some epsilon, shown here. Okay, and you do this many times. You repeat the protocol again and again, and you miss. Okay, every time you miss by a little bit. Okay, and in fact, that circle tells you within a certain number of attempts where your errors lie. Okay, if you look at the average, right, that's that orange vector shown there. That's shorter, okay, than any one of the blue ones, of course, because as was mentioned in the previous discussion, some of these errors are turning into depolarizing errors on average. But notice it's actually well aligned with the black one, a lot better. It's shorter, but it's well aligned. Okay. So in fact, you can look at this a bit more carefully. Here's the same experiment done with actual numerical experiments here. And you can see the orange dots give you the distribution. So here's the projection on Z and here's the projection on Y. And the blue one, of course, is any given one. And you can see what you're doing is you're effectively taking the noise that was spreading out your dots in the orange case and just reducing the length of the vector. So you're really trading this type of noise, which moves you on the surface of the Bloch sphere, to something that causes you to spiral inward or move inward. Okay, and let me. So the next two slides are mathematical. Just to as a grubby experimentalist, I have to show some equations sometimes to make sure that it's believable. So here, if we go to coherent versus static errors, stochastic errors, very formally, rho is your state, right? You want an error map which is coherent, so you have unitaries that actually keep you on the surface. You can model any unitary as an arbitrary rotation, right, along some axis, n dot sigma. And as an example, I'll give you a sigma x rotation, which you can easily write as this matrix we're familiar with. And in fact, in the full 4-qubit space, that will give you this error map here, this error channel here, epsilon. If you cater to the case of small errors, you can estimate cosine and sine as such, okay? And in fact, you see one of them is scaling as theta squared, one of them is scaling as theta, right? That's telling you a little bit about the different off-diagonal versus diagonal elements. If you twirl, if you go ahead and add this randomization, which tailors the noise, you will get rid of the off-diagonal elements that are there, right? Okay, and what you're left with is an error rate that scales as sigma squared rather than sigma, theta squared rather than theta. So that gives you the sense of how the stochastic errors, in fact, will be linearly accumulating and the other ones quadratically. Okay, so how do you measure how close you are to an ideal distribution? Okay, so the metric that we use is called the total variational distance. Okay, so you have some probability distribution, you have some ideal probability distributions. This is a very simple metric that says what's the difference between these distributions taken over all the elements in your set. So to give you a sense that if your DTV was 0, okay, then you have identical distributions, right? Because every element just maps to itself. Here, if you have no overlap, then of course you get unity in this metric. And there's a very concrete example shown here that if your ideal distribution was 0, 0 half of the time, 1, 1 the other half of the time, and your measurement over 1,000 shots gave you these numbers, right? For the distribution that you were measuring, you can easily calculate the TVD by taking the differences. So for the example shown, that's a 7% inaccuracy. Okay, one more math slide. So what does this mean for quantum algorithms, error correction, so on and so forth? You can think about the average error rate as measured by randomized compiling, and that's just, randomized benchmarking. And that's shown here. This is just 1 minus what you get in your error channel on average, okay? And you can look at a measure which is related to the L1 norm, if you like, or this diamond distance. This just takes the difference between your error map and an identity and looks at all the maximally bad values and puts them together. So this is a really worst case scenario. This is perhaps the best case scenario. And you see that's where it bounds your error rates between the scaling with R or scaling with square root of R, between stochastic and coherent errors, okay? So the TVD in this case is upper bounded by the worst case rate, which is this little epsilon of large epsilon. And in the presence of coherent errors only, you will see this square root of scaling. And under randomized compiling, you should see a very different scaling. And that's the physics we're going to look for in the last slide or two. Okay. So here's now a set of hard gates. I'm going to use random gates, okay, on a Fourier transform circuit, say. So first I'm running C naughts. Okay, so these are random C naughts that are run here. And you can see as in terms of the number of 2-qubit gates, which are C naughts in this case, you can see on average, the distance, this is probability of incoherent solution or TVD. Again, 0 being perfect, 1 being really bad. Then you see the bare circuit is somewhere around here for 2 C naught gates. The averaged randomized compiled version is better, right? And in fact, you can start to see improvement even up to gate depth 14 or 15 or say. And in fact, the color coding here gives you the distribution of what's measured. So longer depth circuits can be performed under RC, okay? But the question is, does it really help an algorithm that you would run, okay? And how fast does it converge? So this is the same experiment telling you how many times I actually have to do the twirls to actually get this improvement. Very few, right? If you just go ahead and randomize 5 times, you already see a fairly large improvement. But does it actually help a circuit that you would be interested in? So now I'm going to run the Fourier transform circuit. Okay, so I'm going to run this Fourier transform circuit that had 13 C naughts, if I remember correctly, in this compiled version on 4 qubits. And this is a critical question that Bill was bringing up. What are you observing? So what's interesting about the Fourier transform is that if you start with a very pure input state or very singular state, let's say 0, 0, 0, 0 across your 4 qubits, the output of your Fourier transform is uniformly distributed along all basis vectors. After all, that's what the Fourier transform is going to do. It's going to take a singular function and spread it. On the converse, if you put in something that is sort of a superposition, then you get a very singular output shown here. Okay, so you have this reciprocal property of the Fourier transform. So what I see here is if I run this Fourier transform circuit for an output distribution which samples all my outputs, I see a tremendous improvement in the distance to proper solution. So the error rate or DTV was 22% versus 3% when I did it with compiling. So it was a tremendous improvement. You see almost no improvement when your output is a singular output. And the reason for this is that this TVD depends on the basis in which you're measuring, right? So when you sample uniformly, you will see an improvement. When you sample only one output, you may see an improvement or not. So randomized compiling as evaluated by TVD is very much seen in a uniform distribution. So what I plotted here is distance from a uniform distribution, right, versus how much improvement you'd see in this TVD. So if your output was uniform, you see this tremendous improvement going from bare, shown in blue, to randomized compiled, shown in orange, right? That's very much noticeable across the Fourier transform circuit that are there. If you move away from this, you see a lot of scatter, okay? So in some cases, you'll see improvement, in some cases you won't. But one thing which becomes very interesting is these orange points, which are always done by randomized compiling, lie very nicely along this line. Meaning that if you're a certain distance away, you can very reasonably predict how well or how much improvement you should see. So by tailoring this noise, you remove a lot of the fluctuation in your possible outputs. Okay, and that in this final slide that I have is very much shown here, where I build actually an algorithm simulator from the noise model that I got from cycle benchmark. So I went ahead, I showed you all those color maps, right, of all those different errors are. I can then build a simulation that says, if I have an imperfect quantum processor with those errors, how would it perform, right? So what's shown here is the experimental TVD versus the simulated TVD. And you can see the simulations agree extremely well with the randomized compiled circuits, but not with the bare ones. Again, telling you that all these coherent errors can sometimes help you or hurt you, okay? And in fact, shown again versus the accuracy of your model, even across distributions that are very far away from uniform, you still get a very good sense of how well what is the contribution of your error models to your quantum circuit. So I want to end with this slide because we had 50 minutes. Right? So we're at 8:52 at the moment. For randomized compiling, we have demonstrated an improvement for a significant majority of inputs for the QFT, right? Because most of them produce an output of a certain number of states, and you can see improvement there. We have shown that noise tailoring with randomized compiling allows for reliable simulation of performance. This is also useful. Given a knowledge of the error rates in your system, how good are you at running a particular algorithm? Now, the final question I want to leave with is this really only a problem for NISQ hardware? Right? We started off with this imperfect hardware, lots of errors. Maybe you say in the future, we need 1 million qubits, this problem will sort of go away, right? There will be no utility of this. And perhaps that may not be the case. So what's shown here in this complicated graph, let me take 30 seconds to walk you through it. This is a ratio of the improvement factor of the bare circuit relative to the randomized compile circuit. Okay? So you run the circuit, you figure out what the distance is to the ideal distribution, that's the TVD, and you normalize that to the same experiment run with the randomized compilation. One tells you that you have improved nothing. You get the same, whether or not you do this poly twirling or not. If you see the TVD this ratio being larger, it means that you have improved by randomized compiling. If it's less than 1, then you actually made it worse, right, by doing this randomized compiling. And you can see in blue, that's the experiment over all circuits that we ran, all Fourier transform circuits in 2, 3, and 4 qubits. And most of the time, you see the weight of the histogram is 1+, okay, showing you that you see an improvement. We can do the same thing with the simulation of our error model. That's the gray bars. So those are agreeing pretty well. So then we can ask the questions, what if I make the errors 10 times smaller? Right now we know that the simulator works. Let me just reduce the error rates in my simulator. Of course, much more difficult than the actual experiment. So in the simulator, let me reduce my error rates by a factor of 10. Okay, and in the green one, I reduce the 1 qubit errors by a factor of 10. I mean, you still see an improvement, right? Similar to this. Okay, and if I improve both the 1 and 2 qubit errors by a factor of 10, you see even better improvement in this. So this procedure in general could be extremely useful and scalable for lots of quantum information algorithms. And again, from the pure physics point of view, it starts to give a handle on some of the questions that were raised. How do you get a sense of what errors from the quasi-omniscient observer are really happening in your system? So I'd like to stop here and then, of course, open the floor to questions, handing it back to our MC.
Well, we should give some Zoom applause for the wonderful talk, at least. Yeah, so the floor is open for questions. Well, if nobody's clamoring to get started, I actually would like to ask one. So I wanted to go back a little bit to what sort of Bill was asking about the difference between coherent and stochastic errors. And so the picture that I always had for a coherent error was that if I do an operation, then I don't end up where I wanted, but I always end up in the same place if I run that operation. You know, like this is the over or under rotation. But if I run the same gate, then it's just not quite the one that I wanted. Is that the picture that we have here, or is that only sort of a subset of what are sort of coherent errors in this more rigorous formulation?
No, I think what you're saying is compatible with that, right? So that would be one type of coherent error, right? You're just living on a certain sphere, and then you're sort of just not in the right spot on it. And I think sort of going back to sort of Bill's very good question, saying that measurement really is the key, right? That's your window into the quantum world, right? Whether it's a cubist wave that Rudiger Schack thinks about or otherwise. What's real, I guess, maybe for the experimenter is if you have a certain error, what will be the end after running a certain algorithm, right? And it will be different depending on under the hood if you had a stochastic error or coherent error. And that's what we're really trying to get at this last plot. You run a sequence, right? And you look at the output, right? And then sort of back out. Did you have one flavor of error or not? Because the scaling will be different, right? On any given run, you're right, you can't sort of figure out what's happening, but you're now looking at the ensemble properties and saying that what's the cumulative effect.
Yeah.
So if I could just, this is Bill again, if I could just follow up on Alicia's question. The idea is that whatever the nature of the coherent error, that error, when you apply that gate, is the same each time. Is that a fair description of the model that you have for a coherent error?
There would be one type of error. You could still have, yes, that would sort of cover most of the cases that are there. You can sort of think of more subtle things. Let's imagine that you rotate and your channel is also fluctuating in time. And that's a bit more complicated. But you're right, Bill. So the simplest case that's covered here is not things that are changing in time.
Okay. So it seems to me that in a certain sense, when you do the randomized compiling, what you're doing is changing that coherent error from being the same all the time to effectively being different all the time, and therefore it averages out. Whereas if you didn't do the randomized compiling, it wouldn't average out, it would sum.
That's exactly right. That's the heart of the you're tailoring this, you're doing this.
Right. So in a sense, what you're doing is you're changing the addition of errors from adding the errors linearly, as opposed to adding them in quadrature, which is what happens with random errors. That's the magic that happens because of the randomized compiling. Is that a correct understanding?
Yes, that's absolutely the overarching principle, right? Averaging over Clifford sequences maps any noise process into a depolarizing noise. It starts to get interesting when you prepend that with an interesting sequence, right? Because that's your handle, right? You can measure this kind of depolarizing noise, so you prepend it with different sequences to figure out the error channels. And then you can actually, if you wanted to use it as a protocol to help your algorithms, yes, these errors scale better, so might as well do this.
Yeah, so maybe this is a specious question, but if the errors are stable and if you can measure them, then why not just fix them?
We do that. We do undo them, but certain things are not easily undone by pulse sequence. You don't have enough control handles to do that. So this one, for example, undoing something that's a 4-body correlator or 3-body correlator is not easy, right? Because after all, the control is also not perfect. So if I try to put in a pulse, I will make some other error.
Yeah, but of course that imperfect control, in a sense, is a randomizing process.
Yes.
Okay.
Well, yes, sometimes yes. For example, there's 2 flavors of it. If you have fixed crosstalk, right, which is bad, right, that's not changing. But in fact, you may also have fluctuations on your control amplitude, which is yet another level of noise.
Right, which is both good and bad, because on the one hand, it randomizes things and makes it quadrature sums, but on the other hand, it means that you can't fix it.
That's right. That's right. That's exactly right.
Can I ask a question about this too, Swad? So Irfan, what if you do randomized benchmarking of a gate in question that you concatenate n times? So you have some gate G, you did RB on it, you got some error, then you do GG, you do RB, got some different error, you do GGG, RB that. So will the scaling of the resulting error with the number of concatenations tell apart coherent versus incoherent?
Yes, this is very good, and this is precisely why we got a little bit into this business, because we would run a C0 gate, say, right, once, and say, oh, I have a certain fidelity that allows you to do an algorithm of certain depth, right, if you do a simple-minded explanation. And then you actually run, and there's no way in hell, right? You get close to that, because in fact, you have all these errors, right, that are coherent errors. So yes, and in fact, that's exactly what you're doing, right? You're putting in sequences of different length. You can put in different unitaries, more complicated unitaries, and see what happens. And that's the case for a C0, right? So for example, if we were doing the scrambling paper, then we have a C-sum gate, right? So the gate itself is made up of a bunch of C0s. So when you're doing that, you're essentially doing the experiment you mentioned.
Right. And so the general answer is that coherence error will degrade this composite gate a lot faster with the length than incoherent error.
That's right. And this has been a little bit of debate, right? I mean, not debate, but I would say sort of, truth in advertising in the community, right? Saying that you shouldn't just use your RB numbers. They are correct, of course, right? They are telling you some average error rate. But as you say, if you try to transform that in a system that has coherent errors, you will not get an accurate predictor, right, of performance. So I think this is agreed upon. Then the question is, how does that affect fault tolerant thresholds for error correcting codes? This also is a subtle question, right? So if I have this type of error, what's going to happen to how good my gates have to be? That I think is still, at least I'm not an expert in that, but I think that's still debated a little bit in terms of exactly how that happens. So yes, absolutely. You need a more complete picture, right, of the type of errors. It's the same problem that tomography doesn't scale, right? I could measure in principle for a small system all the errors. I measure the process matrix, and that's it. But in fact, as you start to concatenate the information, you lose something.
All right, thank you.
Can I ask a question? So I think if I remember correctly, in these randomized compiling scenario protocols, there are some assumptions about the errors on the gates. Specifically, you need these errors to be gate independent for at least a subset of gates that you are randomizing. How true is that in practice? I can see that it's improving something, but like from the physics of your device, why this assumption is correct?
Right. So you're right. And in fact, what that translates into for us is that you need very good 1-qubit gates, right? Because after all, that's the thing that you're using to twirl, right? And in fact, if that actually has some other kind of error or is an unknown piece, then you can't use that as a resource. So fortunately for us in superconducting qubits, that's the one thing we can do really well is to make very fast rotations of single qubit gates with very high accuracy. So in fact, we have to be in this limit where, roughly speaking, your 1-qubit gates are at least 10 times better than your 2-qubit gates. Okay. So as you improve your 2-qubit gates, this becomes harder, but nonetheless, you want better than 10⁻³ accuracy on your 1-qubit gates, which is doable. And in fact, to one of Bill's questions, how stable is your system? We had this problem, right? We had to warm up and cool down, and we ran all these experiments, and they stopped working, right? We're like, what happened? Right? That's because there was some drift in the system, and you lost your 1-qubit gates, and it was very clear that the randomized compiling doesn't work anymore, right? For the reasons that you mentioned, Ali Riza. So it's hard to sort of prove what you're saying aside from the very simple sort of case that I have that all of the 1-qubit gates are good.
Thanks.
Irfan, I had a pretty narrow question. You were showing these different gates that you were adding before and after your intended gates. You have these other extra sequence gates, and in the case of the C0, you added sort of different ones. You said, well, this is a C0, so you can't just add Y and some other of the same gate afterwards. And I was wondering, how that works, deciding these different gates when you do these different these techniques.
Sure. So the general principle, Kevin, is that you want to come up with a circuit at the end of the day which was logically equivalent to the first one, right? Mm-hmm. So just like in the vanilla RB, I add a gate and then I want to undo it towards the end. So there's two pieces to this. First, what do you sample from? So you need to sample from a large set, let's say Clifford operations or other operations that are there. So you'll have to run enough randomization that you actually go ahead and look at that set. So that's one element of it. And in fact, I have to recognize a very deep partnership that we have with Joseph Emerson and Quantum Benchmark. So we're using their software. We have a very tight relationship with them. They have very efficient means to generate all these circuits. So that's a whole science in of itself, which I inconveniently sort of swept under the rug. But actually how to generate all of those is something Joseph has mastered. So that's the sampling piece. Now, undoing the piece, it depends on what subsequent operation that you're doing. So what you're doing is you're putting these single qubit rotations, you're sandwiching certain classes of operations with them. So between any two operations, any two of these twirls, something else may happen. So it's not that you're simply exactly undoing the one gate that you put in, you have to undo it after this additional gate operation. All right, so you have to sort of compile it and taking into account what that gate does.
But also you did it with all single, you do it with all single qubit rotations. Is that right?
That's right. So you're calculating the inverse. The inverse when nothing happens in between is an easy thing to calculate. The inverse when some other gate happens in between is calculable, but requires one more step.
Okay. Okay, I get it. I think. Thank you.
Yep.
You said just earlier that your 2-qubit gates are worse than a single qubit, but on the randomized benchmarking data you showed, they didn't look that much worse. I think
that was the coherent error budget. So not just, yeah, no, overall the 2-qubit gate fidelity that we have for a CNOT, on a good day, let's say, right, 996, 997. Kevin, of course, representing an agency that, or at least linked with an agency that I promised 3 nines to. So hopefully we get there soon enough. But yes, you can also do interleave randomized benchmarking. So you interleave, and that's sort of what Lad was also talking about. You put in a gate in between, see what you get. With interleave randomized benchmark, you get rid of more errors, systematics, and then I get 998 when you do that. So it depends on the metric. But single qubit gates always, 10 minus 3, 10 minus 4. 2-qubit gates, in a many qubit system can be quite much lower, right? If you look at some of commercial processors or other things that are available, 95%, 96%, so significantly lower.
Sorry, may I have a question? My name is Alais. I know as a theoretician, I know that there is also a method to mitigate errors using dynamical decoupling when you apply a very frequent field to your device, and if frequency is much higher than change of any coherent interactions, you can suppress errors. So I wonder, is there such an option for your device? Is it possible to add this level just as a before, even before you do gates, just in the physical level to mitigate the errors you describe?
We do it, absolutely. It's important, and we do it. And dynamical decoupling, so again, all of these things have an interesting sort of link to quantum information. So in the scrambling work, which is on the archive, we were trying to realize this gate between Q trits, 3-level systems that are there. Of course, the Barrel group with Chris and Norbert and others did this nice scrambling experiment, right, with pairs of Q bits. So we were doing it with Q trits. So that scrambling gate is complicated because you always have this ZZ interaction, which is on this dipolar coupling, right? And this is a very classic, problem in semiconductors that you can undo with dynamical decoupling. So the first way we tried to actually implement this gate is to actually put in dynamical decoupling sequences, go ahead and do this, and it makes things significantly better. What has come out, I think, recently is the idea that you can sort of compile gates with some kind of flow K picture in mind. So in some sense, what you can do is in dynamical decoupling, you're undoing this interaction with the pulse, right? And you're waiting a certain amount of time for things to cancel, so on and so forth. That's a perfectly good way to also to actually compile a gate. So you always leave the ZZ interaction on. This is great, it's doing something. As long as then you can use that as a resource to put in some other local gates, you can actually compile a better gate. So yes, all of these things come full circle, I think. So general ideas in physics definitely influence each other.
Irfan, actually, speaking of this 2-qubit cross-resonance gates, I wonder what is actually the real limitation to them? Like, basically, why can't you do 4 nines?
Well, yes, we are working very hard on this. So there is a paper out by which we put out with our collaborators, Sasha Korotkov and others, and Vinay Tripathi, a couple of years ago on if you had a perfect set of Q bits, right, with a certain number of levels, 3 or 4 levels, could you get into a parameter regime with the appropriate length of pulse, et cetera, assuming reasonable pulses, what would be the best fidelity? So you can get, in principle, 4 nines or something, or certainly something better than 3 nines. So the next 3 years have been spent trying to realize this experiment. So this experiment means that you need to actually tune the qubits in this case, right, to actually go over all the parameters in the way that we've sort of looked at it. And that's a bit non-trivial. So we've almost completed that experiment, and our goal is to see the scaling. So at least it will tell you which parameter regimes you need to be in, how fast, how coupling, what's the dominant source of error to get good CR gates. So I think the theory paper tells you where you should be. We are not there yet, right? We were using some of those ideas in both fixed qubits and tunable qubits to see that scaling. But one of the dominant errors is leakage to the higher levels. That's one of the things that in the transmon will sort of hurt you. We have a project now that's getting off the ground, running that in flux qubits. And of course, there's someone close to your heart who's now with us, who's also thinking about how to realize that in different types of qubits. And he's also on the call as well, I see. So.
Right, I see. So the leakage to the higher states basically means you have to keep the gate a little slower, and then you hit the coherence stall.
That's right. That's right.
I see.
And there's other, it's subtle, right? When you put in sort of the higher levels and the sort of the many body states that are there, there's other weird things that can happen with modes.